Welcome to Artificial Intelligence for Leaders. In this course, if you're a managerial leader, we're going to cut through a lot of the buzzwords and the hype, and we're going to explain artificial intelligence in plain terms so that you can understand its limitations, you can make better decisions about how to implement it to improve your business and unlock the power of an AI-enabled future. If you're a technical leader, we're going to educate you on how you can talk about artificial intelligence with other executives in your organization and try and open your mind about different applications where you can apply what you know about AI and data science to make your organizations perform better in whatever their tasks are. I'm Dr. Ian McCullough. I bring over 30 years of experience in artificial intelligence in government, academia, and industry. My first day in the United States Army was during the Advanced Warfighter Experiment. This is a time when they were fielding computers to the first tactical units, and I was involved in developing the Advanced Aviation Mission Planning System, which is still in use today. After a brief command in Special Forces and the Conventional Army, I became a professor at West Point with appointments in math, teaching statistics, computer science, behavior sciences and leadership, and civil and mechanical engineering. I established the Network Science Center at West Point, which was the largest and most well-resourced research center at the time. And then from that position, did multiple deployments to Afghanistan and Iraq, advancing technology to improve our operations in those theaters. My final job in the Army was the Chief Strategist for Information Warfare at U.S. Central Command. Following my military retirement, I joined the faculty at Johns Hopkins with joint appointments in computer science and public health, and some of my research focused on social media, so specifically platform manipulation, disinformation, and how social media might be used either for promoting public health interventions or misused in defense applications. I did work in cyber warfare, looking at how we can fingerprint software binaries to identify malicious actors. And I also did neuroscience experimentation. So probably my craziest neuroscience experiment was where I went to the Middle East and I recruited 100 highly polarized sectarian Sunnis and Shias from Iraq, primed them to be argumentative or conciliatory, had them work on a joint task together, all while under neural imaging so that we could understand the neural basis of cooperation and conflict. I was recruited by Accenture in 2018 to establish a federal artificial intelligence practice. Accenture is a Fortune 250 company and probably the largest and most well-respected technology consulting firm in globally. And they do a lot of collaborative work. They consult to Google, to Amazon. They worked with OpenAI in the development of a lot of their ChatGPT and some of their technologies. And so that was a great experience for me. I initially was able to take 50 analysts and grow that into a practice of about 1,200 data scientists, engineers, and AI practitioners with about $1.5 billion in annual profit and loss, and was able to lead the development of 5 of the largest at-scale artificial intelligence program in use for the federal government. I also was able to be a quality assurance director on a number of commercial projects for Accenture. I retired from Accenture in mid-2023 so that I could focus on teaching, developing a AI-based data management, query management approach that eliminates the waste, the risk, the time, cost, labor in the data foundations for most of our AI or industrial applications. And I'm also working in the nonprofit space, working to help veterans with mental health disorders, addiction rehab, and advancing AI and neuroscience research to support that. I look forward to being your guide as we go through this journey on artificial intelligence. Johns Hopkins University is a great choice for beginning your artificial intelligence exploration. Johns Hopkins recently was rated as the best graduate engineering program online by U.S. News & World Report. Johns Hopkins has long been an established name in the area of artificial intelligence and shared autonomy. We have partnerships with Amazon and many other leading AI firms. And we have made a recent transformational investment in artificial intelligence, making Johns Hopkins the largest and most well-funded research institution in the world. Johns Hopkins is also home to the Applied Physics Lab. For those of you unfamiliar with a university-affiliated research center, this goes back to World War II. There were three key technology innovations that were essential to Allied victory in World War II, one being the atomic bomb, another being cryptography like breaking codes and code breaking, and the third being the proximity fuse, which allowed success in the Pacific. And so the proximity fuse was this problem of large sky, small plane, small bullet. How do we prevent Japanese aircraft from successfully attacking U.S. naval vessels? And so they enlisted physicists from the Johns Hopkins University. The first solution was not successful, so they commissioned those physicists, sent them out to the Pacific, and in that theater of war, they actually innovated a solution that was credited as one of the top 3 technology innovations of the effort. Following that, the U.S. Government decided that they needed to be able to have a mechanism to retain top talent to be able to support government entities in advancing technology. And so they created these programs of university applied research centers. There are 15. Johns Hopkins happens to be larger than the other 14 combined and was the original university applied research center. It continues to do work today in the area of cyber operations, artificial intelligence, health, a number of things, spacecraft. So it is a great resource we have at Johns Hopkins University. Our learning objectives in this module, in this lecture, is going to be to define some common vocabulary terms and buzzwords in AI, and I'm going to introduce a framework for managing AI and data science projects called ROAD. ROAD is an easy acronym, and we'll go into more detail with that later in this module. Now, there are a lot of buzzwords that are floating around with AI. This is just a simple word cloud I generated with some of the terms that you might have heard. I'd encourage you to kind of pause, take a look at some of those, and maybe even jot down some of your thoughts. I'd like to begin with a history of artificial intelligence. AI today is a product of time and innovation. And so the first term, artificial intelligence, was actually coined in 1956. And even at that time, it had been a topic of research for quite a while. So we kind of think of coming out of World War II, the 1940s up to 1956, as the birth of artificial intelligence. A lot of it was driven by science fiction writing and advancements that we had in technology coming out of World War II. In 1956 was a conference held at Dartmouth, and some Carnegie Mellon professors at that conference coined the term artificial intelligence. And so even though Dartmouth gets credit for holding the conference, it was really Carnegie Mellon professors that were kind of probably the most active at advancing those ideas going forward. In 1956 to 74, we call these the golden years of artificial intelligence, where a lot of the initial concepts were kind of thought of and developed, and some of the initial applications were discovered. One of my favorites is in 1959, Arthur Samuel, who was an engineer at IBM, he liked to play checkers. And so he thought, hey, I'm going to teach a computer to play checkers with me. And he did that, and he won, and he won, and he won, and it was kind of a boring game. He kept beating the computer. So he had this idea that maybe if I added some elements of probability in the move, that would do something and make the game a little more interesting. And he played, and he won, and he won, and he won, because the computer was making a lot of stupid moves. But then he did something interesting. He had the computer play itself thousands of times so it could learn the probability distributions that led to a winning match. And then he played, and he lost, and he lost, and he lost. And this represented the first time that a computer was able to beat a human that trained it. And he coined that term machine learning. And so 1959 is where we see this term machine learning created. And this was a huge breakthrough in AI. A few years later, in 1966, there was Shaky, was the first mobile robot that was able to be aware of its surroundings. And you see a small picture there of a couple engineers with Shaky. There was also ELIZA, is considered one of the first successful artificial intelligence projects, and it was a therapist that was, you see that's like a text prompt, but it's you could interact with this AI therapist, and it would kind of guide you through that. There was actually another application where they created a mentally ill AI so that Eliza, the AI therapist, could counsel the mentally ill AI, and they could like interact with one another. And so what some of this is showing is the origins were things like introduction of probability and probabilistic tasks, sensors with Shaky, and natural language processing with Eliza. And the applications were very much industrial robots and human psychology or human cognition. So there was a lot of psychologists that were involved in the early developments of AI as well. In the 70s, we went through the AI winter. Now, a lot of this had to do with recessions that occurred in the 70s, so there was restricting funding. So typically when you have a recession, you're kind of going into a period of low innovation investments in that area. Some people had hyped up AI where there was this great hope and expectations, and those hopes were a little bit dashed, right? Where even though you could have a robot aware of its surroundings, it could not safely automate many human tasks. Even though you could design a artificial intelligence therapists, it wasn't, people weren't comfortable with the ethics of that. People didn't want to interact with an AI therapist. And so it failed to meet a lot of the hopes that they initially had in AI. By the 1980s, saw an economic resurgence, and we had another AI boom. And in the 80s, that AI boom was very much focused on expert systems in industry. So these were things to help automate some of the CRM systems. They were reducing error in some of the sales reporting and sales tracking type things, and trying to remove problems with improper product suggestions for clients and such things. So it was very much focused on sales and how to improve sales growth in industry. It was the bulk of those AI applications. Then in the late 80s up until the mid 90s, we saw the second AI winter where, again, these hopes were overhyped and they failed to satisfy. And so we had a drought in terms of AI innovation for another period of almost a decade. And this is, of course, where I entered into the AI space and my view of history begins. So in the mid 90s, we see the age of modern AI. One of the big milestones occurred in 1997 when IBM's Deep Blue defeated the world chess champion. And so this was the first time that a human had been defeated by a computer. And so that made large news and made headlines. And I think it started this whole new hype again of what AI could be. In 2004, DARPA, the Defense Advanced Research Projects Agency, launched what they call the Autonomous Vehicle Grand Challenge. And so this is where organizations could compete for a prize to develop autonomous vehicles that would conduct a race without any human intervention. And so you see a little picture of that down there. I would like to point out that my alma mater, Carnegie Mellon, has won most of those competitions. In 2012, there was another competition, ImageNet, and so in 2012, AlexNet was a winning solution in this competition, and it used what we call now deep learning or neural networks to reduce error rates in object detection tasking in image recognition below 25%. So this was a huge milestone in error reduction, largely due to the introduction of a neural network to be able to do that. And this created a term you might have heard of, convolutional neural networks, or CNNs, or transformer models. But this is where we can actually sequentially train and develop AI models to get better and better and reduce error. That innovation allowed, by 2017, the birth of deep fakes. And I think one of the early deep fakes was of President Obama. And so you could fake, make a video that looks like a famous person talking and acting, but it's actually generated by somebody else, right? So it's just kind of faked. This also led to the growth of what we call transformer models. And so transformer models will go into more detail later, but it's basically where you can train an AI algorithm to do basic tasks like recommend a person, and then fine tune it to recommend to identify a specific person. And so there's a lot of things we can do with these transformer models, which has really opened up the application areas for what we can do with AI. And then probably the most recent is generative artificial intelligence. This is where AI now is able to get involved in automating creative tasks like writing a piece of software code, or identifying vulnerabilities or automated repair of vulnerabilities, or can write your kid's high school English essay for them. Now there's some limitations with that, but that has captured the attention even more. And so we've had these major advances, milestones that have occurred close together recently that has kept that AI hype cycle going and probably accelerating. And so a big question remains, what is the future going to look like? Are we going to move to a further AI-enabled future, or are we headed for the next AI winter? So Gartner tracks these pretty carefully in what they call the hype cycle. And so the idea is that if you look at the y-axis, the vertical axis there is expectations, and the horizontal axis is time. And so there is some type of innovation trigger that leads to a peak of inflated expectations, and then you have this trough of disillusionment, and then slowly people kind of get to this plateau of productivity as they balance expectations with disillusionment and kind of come into what's actually useful and productive. What we would like to do is prevent you from having inflated expectations with AI, be a little bit more realistic, and hopefully then you won't have such a trough of disillusionment, and maybe we can move in a more responsible way from innovation triggers to how we can actually put them into productive use in industry. And in doing so, we can prevent one of these AI winters going into the future. Why is AI continuing to advance, and why is it doing it now? What has been different in modern AI versus the previous AI winters? And we really credit that to three things. The first is data. There are tens and tens of thousands of data, and we have the computational processing power to work with large data volumes. So this exponential rise in data is collected through more and more things. Think of the Internet of Things, think of your iPhone, think of your Alexa in your house, think of all of the other areas in which we're getting new data. That has allowed AI to be trained on a much larger volume of data. The processing power has advanced. We have advancements in microelectronics and semiconductors, and we are able to have much greater processing power than ever before. And then the cloud allows access for people to work with AI without having to be at a university or a large industry. So cloud is basically renting somebody else's computer, and it allows you to take advantage of the data and the processing powers that exist. So as we've been talking about AI, what is artificial intelligence? So I've given a couple different definitions that I think are interesting. So the European Union basically defines it as a machine-based system, and it's going to operate with varying levels of autonomy, that's going to do tasks such as predictions, recommendations, or decisions that influence physical or virtual environments. And in your reading, you can look at the EU AI Act to get more information on that if you're interested. I contrast that to the Chinese government's definition of artificial intelligence. And so they're going to define that as the theories, methods, and technologies, right, as well as these digital computers or digital controlled machines that are going to simulate or expand human intelligence, perceive the environment, acquire knowledge, and use. So you'll see that there's a little bit of a difference in the way that they think about that. And I guess my point here is that there's no universally accepted definition of artificial intelligence. It's all kind of in the same space. So I'm going to give you my definition. My definition is simply sense, comprehend, act. Those are the three components that make it AI. There is something that is perceiving the world. This could be just simply scraping a data that is in a database somewhere and sensing the elements of that data. Or it could be a sensor that detects you coming up to the grocery store. The comprehend could be a fancy algorithm of what are we going to do with that data to predict something that happens in the future. But it could also be, to extend that grocery store example, simply understanding that you are approaching the door and need to enter the store. The action then could just be as simple as opening the door, automating that piece. Or it could be informing a human action with that predictive analytics, like you should buy stocks now, or you should order new inventory today. And so those are the essential elements of AI: sense, comprehend, act. Now the dash line says that there is this optional step that we can include in artificial intelligence called learning, where that action can have some sort of feedback mechanism that allows us to sense better, allows us to understand and analyze better, or allows us to improve our actions. And so that is a learning step where something on the outcome, maybe it's that action, is improving the way we sense, comprehend, or act. But at its basic element, most essential pieces, artificial intelligence has to have these three components of sensing, comprehending, and action, and that action can be informing. Now, AI is often powered by machine learning, another concept you're going to hear about. And machine learning is basically where you are going to improve in that AI process with future data, future feedback. And so machine learning is basically at the basis of that. This is showing you a chart of different applications that we can use for artificial intelligence or machine learning. And so what you're seeing is in the center is this idea of machine learning. So again, algorithms that allow learning. We're going to go into more detail of what that is. And then there are AI capabilities that complement machine learning to improve how we're going to comprehend, reason, or predict or optimize constraints. And then on the outer layer are AI applications, things that we can do with AI because of that, right? So if I look at augmented reality or virtual reality in the upper center left of this diagram, you've all seen the goggles and you've seen the virtual reality. I'm doing work with my nonprofit right now where we are using generative AI, right? So to create environments for veterans that are dealing with PTSD so they can do exposure therapy. So they can speak about their experiences. We can speak into the generative AI, create a virtual environment, and then have the person go through that environment. And we're using computer vision to detect facial expressions that allow us to understand emotional feedback neurologically in the patient that will allow us to moderate the way that we actually go through that environment. Now, there's this machine learning piece of how have we been able to actually create that generative AI environment? Well, it's required a lot of data and a lot of trial and error and learning about how certain words represent virtual environments and how we actually can display those. How we're actually able to get the facial expression so that we do not do additional harm and we can actually maintain the right the right level of psychological input so that we can improve therapy. And so there's detecting, sensing the facial expressions, understanding and reasoning about what emotions those are eliciting, and then providing the feedback to the therapist to be able to control the setting. And then the augmented reality is the actual hardware, the goggles, that is then enabled by that. Well, this path, right, this simple example, allows us to not only treat veterans that are suffering with PTSD today, but it allows us to better understand the risk factors to inform resilience training and help protect future veterans from having to deal with as much of the horrors of warfare. So hopefully that's just a simple example of how some of these different patterns fit together. And as you kind of pause and look through some of them, might spark some other interesting thoughts or ideas for you. So let's get back to terminology. There are four basic concepts here. We've talked about artificial intelligence. We've talked about machine learning. Machine learning, we would say, is a subset of artificial intelligence. So there are certainly examples of the door when when you're walking the supermarket and the door senses you're coming, opens, recognizes you're trying to get in the store, opens the door for you. There's not a whole lot of learning, right? That's a pretty stable application of artificial intelligence today. Machine learning would be if it's doing something to get better as it gets more and more data from you. Deep learning is this idea of sequential improvement in models with adding different layers to it. And data science may overlap deep learning, machine learning, and artificial intelligence, but it also involves kind of established statistical methods that don't necessarily have anything to do with that sense or action piece, right? So data science is a slightly adjacent term. So let's go into more detail on artificial intelligence and machine learning. So we can break artificial intelligence down into narrow and general artificial intelligence. Now, general artificial intelligence is the idea of automated consciousness, that the machine is self-aware, much like our human thoughts. Now, this is in the realm of science fiction. There is absolutely no indication that is trending in any kind of serious way. The idea of general artificial intelligence is an aspirational hope that people would like to get to, but as of such, it remains science fiction for now. Narrow artificial intelligence is where we're using analytics, algorithms, automation that seems to be resembling human thought or is inspired by human thought in some way to achieve some type of task. That narrow artificial intelligence can then be broken into probabilistic-based approaches, right? So basically using uncertainty and statistics in what we would call machine learning. And then there's rules-based expert systems or deterministic AI, which is the area of symbolic AI. Symbolic AI was some of the earliest approaches. So when you think of ELIZA or Shaky, it was basically sensing inputs from its environment, and it had a certain set of rules. If I get this input, then I'm going to do this. If I get that input, then I'm going to do that. Well, one of the problems is you couldn't necessarily think of all the potential inputs that a human could give it. And so when we came over to this area of machine learning, the idea of Arthur Samuels adding probabilities to some of the decisions you're making allows you to not be as rigid, but it allowed this huge leap in your ability to take uncertain data in and reason about it and kind of make what's the most likely output. It requires data and a strong data foundation. And so what do you do with the data? Well, there are three areas here that we're going to go into more detail with. Supervised learning is basically where you as a human have the data, you have gone through and labeled the data, so you're telling the computer what the data means, and then giving it back to the computer so it can learn how to do that without you. Unsupervised learning is where you're asking the computer to identify patterns and show you so that you can maybe help with the labeling. And reinforcement learning is where you have a human in the loop or something where it doesn't have to be a human, but you have some sort of feedback mechanism in there so that as it is taking its data, applying its model, there is some sort of reinforcement where, yes, that was successful, that was not successful, and you feed it back through. So as we go more into machine learning is essentially the study of data-driven algorithms. And so we talked a little bit about this, about their supervision. So supervised machine learning is where you've gone in and labeled the X's and O's in this example, and you are going to teach a machine to be able to determine when they see future data, is it an X, is it an O? When we deal with unsupervised learning, we are looking at patterns in the data. In this case, it's identified 3 clusters, and then we're asking the human to come in and make sense of those clusters. So instead of the human labeling up front, we show the pattern and then let the human label it, whereas in supervised, we label first and then see how the computer performs. And then the reinforcement learning is where we are going to have some sort of as the process is going, we're going to have some sort of intervention or some sort of reinforcement that occurs. So an example of reinforcement learning that I did at Accenture was for insurance companies. So the insurance company has to give it gets customers that will fill out a bunch of information about their driving habits and driving records, and then you have to render a quote for how much you would charge them for auto insurance. Now, there's a bunch of other competitors that are in that market, and so you have to assume that that customer is getting multiple quotes. So is yours going to be taken? You want to have it high enough so that you're making profit and you're mitigating your risk if you have to have a payout from insurance, but not so high that you lose your customer. And so figuring out where that sweet spot is an analytic task. So you don't, because you don't get to see what your competitors are doing, you just have one reinforcement or one reward, buy or no buy. And so we can enter that into the analytic equation so that we can improve the performance and maximize the quote that we can actually offer a customer and still get a customer accepting our insurance or becoming a client. To give you a more rigorous definition of machine learning, I'm going to use Mitchell. He's probably one of the first textbooks in machine learning. So his machine learning textbook is probably the most authoritative source for what machine learning is. And so his definition is that a computer program is said to learn from experience E, any experience, with respect to some class of tasks T and measured performance P, if it performs at tasks T as measured by P, improves with experience E. All that's saying is that you have three elements. You have experience over time, you have a set of tasks, and you have some sort of performance measure. And if the performance measure gets better and better as it gains experience doing the tasks, you have machine learning. The two things I would like to just highlight here is that machine learning, right, because it is probabilistic, there is built-in error which creates the opportunity for bias and variance and hallucination, and it means that every time you run the algorithm, you're not necessarily going to get the same thing. It means that if you have biased training data that is going into the machine learning algorithm, that can adversely affect the outputs or the things that are coming out of it. When you look at the deterministic AI, the symbolic AI, it's accurate. You can mathematically prove that it is accurate and that it's consistent, and there's a lot of mathematical properties that you get out of that. But it isn't necessarily going to be able to do all tasks. So my belief is that we need to figure out when is the appropriate application of probabilistic machine learning versus deterministic symbolic AI, and how do we use them together to get maximum outcomes. Now, data science is another common term that people are using. This is an interdisciplinary field, so it's not just math, it's statistics, it's computer science, but it's also public policy, sociology, things you wouldn't necessarily think of as analytical, are increasingly using analytic methods to address applied problems. So it's an interdisciplinary field, and it uses the scientific method, which is, if you observe the world around you, you do need to form a hypothesis that you can then test analytically. So that's kind of an essential element of data science. But it's using the scientific method, processes, algorithms to extract knowledge, insights from noisy data. So there is a spectrum that goes here from hindsight through insight to foresight. And there are kind of four basic tasks that you're going to do with data science. You're either going to do something descriptive and kind of do an accounting task to describe what has happened in the past. You're going to do something diagnostic to try and understand why something happened the way it did, that is going to give you perhaps insight into what levers or decisions you can make as a leader to improve your business. Or you can be predictive to forecast what is going to happen in the future if if things continue as they are, right? So if I look at historic sales, I do nothing different. Predictive is what's going to happen in the future. And prescriptive is if I can understand the levers and the factors that make things better or worse, can I have the knowledge to say what will happen if I make this decision, or what will happen if I make that decision? that's prescriptive. And so those are kind of the four things that we're using data science to understand. It's primarily done for improved decision support. Now, I show you this picture. I'm from Tacoma, Washington, where the Narrows Bridge is, and it's a famous example of a bridge that completely collapsed before I was born, but it's in my hometown. And my point here is that people were building bridges long before there was a scientific discipline of engineering. And just because a bridge failed didn't mean that engineering was a bad idea or that a bridge was a bad idea. It just meant that it could be built better. And so as with technology, there is no established, universally accepted standards for artificial intelligence. And so there, just like any technology, AI can be built well or it can be built poorly. And there's a lot of risk involved in building it poorly. That doesn't mean that we need to overregulate it, and it doesn't mean that we need to suppress innovation. It just means that we need to be careful, and we need to go into AI technologies with our eyes wide open so that we can properly appraise the risks and not get that overinflated hype cycle or allow ourselves to fall into that trough of disillusionment. So right now, today, we are at a crossroads, I would argue, and we are either going to head to an AI winter on the left or an AI-enabled future on the right. And what faces us at the fork is this technology valley of death, where innovation and ideas don't actually get transferred into useful application. And that's what this course is all about, is navigating that technology valley of death. I like to highlight a couple things, right? And so, first of all, I'll point out that these images have been generated with generative AI. I just thought it was an interesting application. I would tell you that nations like Russia and China have already decided they're going to head down the path of AI-enabled futures. And they are advancing technology at a rapid rate, and some believe that they are ahead of the United States and Western nations. When you look here at the left, nations like Japan, Singapore, the European Union have all adopted AI regulations that I would argue are overly fearful. They are hyper-focused on risk and problems, and they don't necessarily look at the hope. And so I'm just going to give you a real-world example here. I supported organ donation. We'll talk about this later in the course. But the Organ Procurement Transplant Network basically runs the system to decide who's going to get an organ, a deceased donor organ for transplant as one piece of this. So what I discovered in a project was that there was a human bias, we called it optimism bias, where if you've been on the wait list for an organ for a while, you're going to get offers more regularly, right, and more frequently. And so humans will think that there's maybe a better organ that's going to be offered next week or a couple weeks from now. And so instead of adopting, of accepting an offer for a deceased donor organ that's perfectly good today, I'm going to choose to wait for a better organ. Well, as so many people are saying no, before you get to somebody that will actually accept the organ, in 2022, 27% of viable organs for transplant were discarded in the trash, while over 5,000 people died on the wait list. We were able to implement an AI algorithm to just help inform decision makers at transplant centers what the realistic likelihood for machine learning would be of how long it would be to get an organ that is, 20 points better, 50 points better, varying levels of better, and what the patient's mortality outcome would likely be without the organ today. And that allowed doctors to make decisions faster, better, and in doing so resulted in 3,000 additional organ transplants in 2023. And I like this example because if we had adopted the risk-based regulations of Japan, Singapore, and Europe, we would not be able to implement that outcome, and there would be 3,000 fewer transplants and thousands of human deaths as a result of those regulations. Whereas if we recognize that humans are flawed and humans make mistakes and say, how can we use that human baseline And if we have an artificial intelligence technology that can help that do better, is it not unethical to withhold that AI technology? And this framework is, I think, the biggest question in helping us look at where do we go, the AI winner or the AI-enabled future. I highlight these two quotes, right? Adam Smith said, "People fear what they don't understand and they hate what they cannot conquer." And I would say that fear and ignorance are the architects of stagnation, and they stifle the steps to a better world. So I hope that as we go through this course, you can have a more realistic frame of what artificial intelligence is, and I hope to guide you to an AI-enabled future so that we can actually help those in need and make our world better through AI. I'm Dr. Ian McCullough, and this has been our first lecture in Artificial Intelligence for Leaders.